Right, welcome to this bit. What we want to do now is we want to continue on with that problem that we spoke about in the last one, just recapping it. It's going to be NaOH dissolved in 250 mils of water to prepare a titrant. So what we're doing is we're preparing a titrant over here, right? So let's put in what we're doing at the top. We're putting NaOH, we're putting NaOH plus water, right? Together. So we are dissolving, and let's see what have we been given. Okay, they've said to us 30 grams is dissolved in 250 mils. So given, let's just go through the process. Molecular mass, number of moles, concentration, and volume given over here is 250 mils. Okay, so what's the molecular mass of NaOH? We say, okay, it is 40 grams per mole. Like so. Calculate the number of moles, 0.75 moles. Okay, just put that a bit better. Concentration, therefore, is N over V. Change this to 0.25 decimeters cubed. Therefore, my concentration is going to be 3 moles per cubic decimeter. It's also m dm cubed, moles dm cubed, right? Same thing, right? Now, let's read on what they say. This is over here, okay? This is our titrant, isn't it? That's the titrant over there. So what we're now going to do is we're now going to, we're going to use this. Then they say to us, okay, this is used with prepare the titrant, 25 moles of H2SO4. We use 16 moles of the titrant and it neutralized the acid. Right, now let's have a look at our titration reaction. It's NaOH, okay, it's going to be NaOH plus H2SO4, okay, is going to go to Na2SO4, okay, plus 2 H2Os, okay. This is our actual reaction now, isn't it? This is the neutralization reaction. We get a salt plus water. Acid, base, salt, water. Remember that from way back? Acid, base, salt plus water. Okay, so now this is the one we're using. So let's put in our recipe for this guy, shall we? Let's say the recipe here, I have to make sure if I've balanced it. No, I haven't. There's a 2 over here. So we can put the recipe in now of 2, 1, 1, 2, like so. Right? Let's now draw our line underneath that and say, right, now let's put in given. Okay, given in this case, right, we say, oh, hold on, we've got a bit of an issue here because we know, let's just check, 16 moles of the titrant. So 16 moles of NaOH was used, correct? Okay. We say neutralize the acid of 25 moles of H2SO4. Okay, that's what we know. So therefore, molecular mass and number of moles. But now let's ask ourselves, okay, there are, okay, 3 moles in every cubic decimeter, aren't there? So in this cubic decimeter here, okay, well, let's rather say this one. In this cubic decimeter, there's 3 moles. But we are only using 16 milliliters out of there. Okay? Which means that we've got to account for the difference in the number of moles, haven't we? We've got 3 in here, but we're only taking a small chunk of this. So there won't be the same number of moles. So we now have to account for that. So we say, right, therefore, the concentration, right, concentration is equal to 3 moles per 1 cubic decimeter, right? Okay. But that is going to be in 0.016, okay? Correct? Because 16 milliliters, remember, 1 liter, right? Let's just do this conversion over here. 1 liter is 1 decimeter cubed. 16 mil, I've got to divide that by to get that, okay, to liters, haven't I? Not 1,000 liters, Kevin. I was thinking in terms, trying to get to milliliters. 1 liter is 1 cubic decimeter, isn't it? All right? There I've got milliliters. I've got to get that to liters to do the conversion. So I have to divide that by 1,000. So I'm actually saying that the volume I've used is 0.016 liters, which is the same as 0.016 cubic decimeters. Okay? Similarly, my H2SO4 volume is going to be 0.025 decimeters cubed, isn't it? So we've done that conversion. But now we've got 3 moles in there. So how many moles have we got in there? We now have to work it up. We say to ourselves, right, the concentration, okay, is going to be equal to N over 0.016. Concentration is number of moles over 0.016, and the concentration was 3 moles per cubic decimeter, right? So if we do that calc there, then we say, right, therefore I can now work out the number of moles is 0.016 times 3 is going to be 0.048. 0.048 moles were used, correct? Okay, because that's how many moles were in that little sample that we took. Remember, we mixed a cubic decimeter and it had 3 moles in there. We took a little bit out. The little bit out says we only had 0.048 moles in it. Okay? Now we say, right, therefore, we go back up and we say, okay, whoops, go back up and we say, right, now do we know number of moles? Yes, we know number of moles. So let's go and work with that guy. So, okay, we know U. Let's go back up then and we say, okay, so 0.048 was how many moles I've got of U. Okay, number of moles, right, from there. Therefore, now we apply recipe, don't we? Apply recipe, 2 to 1. So this is 0.024 moles of that was used. Therefore, now we can continue the calc with him. I'm just going to put it down over here, if you don't mind. Okay. We've got the volume we've worked out. Therefore, the concentration of the acid is going to be equal to 0.024 divided by 0.025, which is equal to 0.96 moles per cubic decimeter, right? I just took the number of moles and divided it by the volume of the acid, okay? Very, very straightforward, as long as you just stick to the table. And realize that when you're manufacturing a titrant and using an element of it, right, once again, just to recap it, there's 3 moles in there. The little bit we took out, we have to work out how many moles are in him, or in that sample, don't we? Okay. Right, let's have a look at a slightly different one then, right? The slightly different one over here is the next question. It says, okay, let me just look for my titration one over here, okay. Okay, what I'll do is I'll get another titration one slightly different, and I'll come back to it. Because question 3, I thought it was a titration one, but it's not. We'll put another titration one in. Discuss the concept of an ampholyte using a diprotic acid, such as sulfuric, and an example illustrate how water is an ampholyte. Okay? Ampholyte can accept or donate a proton, hence it can act as an acid, donating, or a base, accepting a proton. And they've said using a diprotic acid, right? So we would say H2SO4, right? That degenerates to HSO4 minus, correct? And then it goes to another H plus, like so, plus SO4 minus 2. The overall reaction is actually 2H pluses plus SO4 minus 2, isn't it? That's what's actually happening over here. That is dissociating with 2 hydrogen protons coming off that, and it's going to obviously join with 2 water molecules to form 2 H3O pluses, isn't it? Now here is where we would say, right, at this point, this HSO4 can donate further, so it can continue acting as an acid, or it can accept a proton and go back that way, and it can act as a base. Okay? So basically that's what we're going to say with that one. Then they say, okay, all right, the overall reaction is this. So yes, let's just have a look at the overall reaction. H2SO4 dissolving in water, okay, to form an aqueous. So this is a liquid, well obviously. To form the aqueous solution goes to 2H3O plus SO4 minus 2. Why? Is because those 2 there have joined onto 2 of those guys. All right? We needed 2 of those to join in there. All right. Right. And why can water be used? Well, once again, water. Let's look at how water is going to look. Water is going to look as follows, isn't it? Okay. It's going to be H2O plus H2O plus H2O, like so, giving us, remember we've seen this one before, H3O plus OH minus, right? So what have you got here? We've got a situation where water can either do the H, can donate from there to form OH minus like that. So this is donating there, and the other one is then accepting it, isn't it? So you've got water is proton acceptor and a proton donor, right? It can go both ways, right? That's quite a straightforward example, essentially, of the situation. So it's a pity I didn't have the other titration one. I thought I did have one. Just let me have a very quick look and see. No, I don't think I did put in another one. Okay. But anyway, okay, we'll come back and we'll do another titration one, because they're quite important and they're not that difficult to do. Okay, let's just have a look now, and because where we're going in the next section is we're going to be going into redox reactions. So let's just introduce the redox reaction at this point, shall we? We've got a few minutes on this section, and I'd like to introduce it. The redox reaction that we've got is you know that redox stands for reduction and oxidation, or oxidation reduction reactions. Let's just think, what we've just seen in acids and bases is we have seen essentially a proton being donated from an H-rich environment, HCl, H2SO4. We've seen a proton being handed over. But remember that in early stages of chemistry, we discussed the electron. We've done a lot of work on how they bond, where they go, how they sit, the nitrogen, and then the 3 hydrogens coming in to form NH3, etc., etc. So all in all, what we've got is we've got electrons are being given across, they're being shared, aren't they? All right? So in an oxidation reduction reaction, things are going to involve the electrons. Let us look at one that I've got here. We said magnesium and zinc chloride react to form magnesium chloride and zinc. And there's a few questions they're going to ask us, right? So let's have a look. They say magnesium and zinc chloride. So let's write it down. Mg solid plus Zn Cl, okay? Now we have to just check, that we got it correctly balanced. Zinc, what is the valency of zinc? Well, if you're not sure, you can always look on the tables where they give you the half reactions, and in there you'll see that zinc is Zn plus 2. So over there we've got a Cl2, all right, and they react to form Mg Cl2, okay, aqueous plus Zn solid. Okay, and this is solid and that's aqueous. All right. Now, once again, what we've got here, let's just look at the situation. What actually have we got on this side? Right, we have got an Mg that is solid. We have got a zinc that's aqueous. If it's aqueous, what does it mean? It means it's in its ionic form. It has dissociated. So it becomes a Zn plus 2 ion. This is a solid, right? That's an ion, it's in aqueous. And we've got Cl minus, and we have got 2 of them as ions, right? Because the zinc, Zn, floats off as a plus, and then there's 2 Cl's. So there's a Cl goes there and another Cl goes there, right? When it dissociates, that's what it does, doesn't it? Now, let us have a look. What have we been told we've got on the other side? We've got here MgCl2, which means we must have Mg plus 2. This must be an ion, correct? And we've got Cl2, so we've got 2 Cl minuses there to form that. And we've got Zn solid. Now the question comes here. Okay? So far so good, because that's obvious. We had that in the water, zinc chloride, right? That was dissolved, so it was ions. And then they've told us on the other side we end up with magnesium chloride and zinc solid, right? Well, what happened? The solid zinc changed to an ion, okay? All right, let me just fill this in. This one changes to a solid, and this one is an ion still, right? So what happened is the solid went to an ion and the ion went to a solid. How could the solid change to an ion? It must have dissolved, right? Just think of it like that. It must have dissolved. So what did it do? It dissolved in the water. When it dissolves, it forms an ion. What happens? The electrons go, don't they? Think about it. It was a solid, it's now an ion, so there must have been 2 electrons floating around somewhere, correct? What did zinc do to change from Zn plus 2 to Zn with 0 charge, right? Okay, maybe I should be using a different color. Let's use red. I don't want to thingy. Zn, okay, was a plus 2, so it must have got 2 electrons to have a 0 charge up there, correct? Can you see that those 2 electrons there came from that side? This one here wasn't affected in any way. So this is called the spectator. Spectator ion is over there, right? It wasn't affected. It didn't gain or lose any electrons. But what happened was this one lost, this one gained. And this means there was an exchange of electrons between the two. What does that mean? That means that the electrons have flowed from the one to the other one. They have been handed over to the other party. Then the zinc would become the solid. And what do we say? There's an old saying, oil rig. Okay, oxidation is loss. Okay, reduction is a gain. So we look who loses, and we say, okay, magnesium lost here and zinc gained. So in this case, oxidation is loss. So magnesium oxidized and zinc reduced. Okay, so when we're looking at these reactions here, what we do is we go through the process. It's just a way that I like to do is I say what happens, and it's not always dead straightforward to do it that way, I grant you. But we've actually worked out here what has actually happened and who's oxidized and who's been reduced. Also, you're going to get reducing agents, oxidizing agents and things. I personally prefer always to work out which one was oxidized, which one is reduced, and then the opposite, it becomes the agent. So if it's oxidized, reducing agent, reduced oxidizing agent, right? So that's the way, I work it backwards the other way because it makes more sense, because then I can apply oil reg to it. What is the last thing we have to do? We said, well, okay, we are now going to put these two reactions together, okay? So I say, all right, well, let's just add them then, shall we? We've got Mg solid plus Zn plus 2 plus 2 Cl minus plus 2 electrons, there they are, and that is going to go to Zn solid plus 2 Cl minus, okay, plus Mg plus 2 electrons plus 2, over there, there's my ion Mg, and now can you see we've got 2 electrons on each side. That means that what we can do is we just cancel them out. Okay, because 2 were given and 2 were taken, so they're not in the equation anymore. Therefore, we end up with a final balanced reaction for the equation. We end up with Mg solid plus Zn Cl2 going to Zn solid plus Mg Cl2. Okay, simple as that. Okay, those are the redox reactions. And we're going to do a couple more of those, because what I want to do is to put them into an acid medium and to see which one is which. And we're also going to have to look at oxidation numbers as well. But we'll do that in the next one. What I'll do is I'll do a titration, and then we'll carry on with the oxidation reduction. Or maybe just carry on with the oxidation reduction, finish that, and go back and do an extra titration for you right at the end.